Even, okay. Okay, so I heard that yesterday you didn't do enough math, and so we're going to do a bit more today. I'm joking. um, Hi, I'm Lisa. I am a scientist at MIT, and uh, yesterday was really nice to talk to some of you. I know many of you have a background in theoretical physics, and so I thought I would start this lecture by saying that one day I was also a theoretical physicist, and my dream, that is about 20 years ago, was to contribute to increase the knowledge of humanity by studying how you could unify gravity and quantum mechanics. And I imagine, I think this is still a hot topic 20 years later. My story is that by chance, I grew up near one of the gravitational wave detectors in Italy, Virgo. And when I walked into the control room of Virgo about 20 years ago, the interferometer was not working. And I was like, whoa, and now what am I going to do? How am I going to detect the graviton and understand the quantum nature of gravity if the interferometers do not work? And that's when I discovered something that I want to share with you today, which is there is a world out there, outside theoretical physics, or actually some of this work, the skills that theoretical physicist has are actually quite useful, as you would see, mostly because interferometers are very, very complex instruments. So in our imagination, like for, the big telescopes, at least the way I think about it, in the astrophysics world, you build a telescope, you put it out there, and then it works, and that's it. And then you just analyze the data. The field of gravitational wave instrumentation is relatively new, and so actually to operate and improve the gravitational wave instruments, it takes a lot of work. And it takes the expertise of many different type of people who come together to overcome the challenges. And so this is what my talk is about. It's obviously just 1 hour and 15 minutes, so most of the topics will be just, just giving you an idea of what the problems are. But Matt and I were very happy to talk with you more about this. Matt is also one of those who thought he was going to unify the theory of gravity, and he also ended up working on the instrument. We all started like this. Great. Okay, so the outline of my talk is I will start with some instrument basics, and then I will give you some highlights of the instrument performance from the past observing runs. And then I'm going to spend some time talking about, I hope, interesting, relatively new technology that gravitational wave detectors are using today to improve their sensitivity, which is based on quantum optics. And then at the end, I will go from the past back to the present and the future, and telling you what's happening right now at the LIGO Virgo sites and what's coming next in let's say, within this decade. So for an instrumentalist, I can actually summarize everything that Barry and Alessandra said yesterday in 3 slides. So the first one is the basic concepts of general relativity. If you want to really, obviously the math gives you the power of using general relativity, but the basic concept, the way in which I like to think about it, is that the revolution of Einstein general relativity is that gravity isn't anymore a force that acts in space and time, but instead is built into the actual structure of space and time. That's the key insight. And maybe the most elegant way of saying this is that space-time tells the mass how to move, and mass tells the space-time how to curve. That's the way in which I like to think about it. And then one of the main pieces of general relativity is gravitational waves. And as you've seen yesterday, thanks to general relativity, you can calculate what's the amplitude of the gravitational waves, which is equivalent to say what is the perturbation of the space-time produced by the gravitational waves. And the whole point is that this perturbation is small. That's the key thing, because it's big G divided by the speed of light at the 4, where here is the amplitude of the gravitational waves, and it goes as 1 over the distance to the source. You have seen all of this yesterday. And so for typical astrophysical sources, the point is this H goes as 10 to the minus 21. And then, you've seen this again yesterday, if then you want to try to measure this, if you then want to try to measure the displacement and the stretching and squeezing of space-time produced by this wave, what you have to measure is the displacement that is proportional to this amplitude. And that's what kills you, essentially. Because even if you then are able to put your masses very far apart, even if it's a kilometer apart, the displacement that then you need to measure is 10 to the minus, of the order of 10 to the minus 18 meter. There is no ruler on Earth that can give you this precision. And that's why it took many, many years for gravitational waves to be measured, just because this is a very difficult measurement to do. There is a movie that maybe you have seen. It became very popular right after the gravitational wave detection. Let's see if this works. Yes. This is the basic concept of a Michelson interferometer. Gravitational waves arrive, and they change the interference pattern of the light at this port that we call the dark port. So let's go slow. There is the electromagnetic wave from the laser that is split at the beam splitters, is reflected back by the two mirrors at the end. And this is what we call the dark port. And you can control the relative distance of this mirror with respect to the laser such that there is no light going out toward this port until the gravitational wave arrives. The space-time is distorted, and it's equivalent to a relative motion of the two mirrors, and the amplitude modulation here at this dark port has encoded all the property of the gravitational waves it has produced. So that's kind of the idea, and this is a photodetector that converts the light that arrives in current, and then you can put it across a resistor, get a voltage, and that's the signal out that we measure. So this gives you, I guess, the overall picture of how it works, and then, as they say, the devil is in the detail, and there are a lot of details, and so I'm going to go through some of those. First of all, we give all of this for granted, but this is actually intuition that several people in the world started having in the 60s, that this technique, so using a laser Michelson interferometer, could be the way of trying to measure 10 to the minus 18 meters. The person that we usually attribute a lot of the credit is Ray Weiss, and the reason for that is in 1972, he wrote down what then became the original concept of LIGO, the Laser Interferometer Gravitational Wave Observatories. And remarkably, he had already figured out in 1972 many of the fundamental ingredients that a large gravitational wave detector based on laser interferometer should have. And here are some of them. The first one is long arms, for the reason that we just said. You want to make the stretching and squeezing of space-time as large as possible so you can measure it. And the length of the arms act as a amplification factor for your H. There is nothing you can do about H. That's the nature of gravity that determines that. But you can make the arms as long as possible. You understand there are practical reasons why on Earth you cannot really make it as long as you want, mostly cost, actually. The other key ingredient is ultra-high vacuum. And the reason for that, Barry mentioned that yesterday. So you have your laser beam that propagates through the end mirrors, and if you had air in your system, the molecules of air would scatter your light away, and so you could not make a measurement. At least this is one of the reasons. And then you need suspended mirrors. Mirrors needs to be able to move and sense this distortion of space-time. And then you need high laser power, and we'll talk about why you need that high laser power and what high really means. So we talk about long arms and ultra-high vacuum, so let's look a bit more in details why the mirrors are suspended. Maybe that's obvious to most of you already. So this is a bit of math, but not much, for those who like it. And then I have a movie for those who don't like math. So this is your pendulum, and this is the mass at the bottom of your pendulum. The position of this mass is x, and you can write the equation of motion of this mass with respect to the position of the top of this pendulum. And then you can, this is really just F equal ma, and then you can do a Fourier transform, and at the end you get this expression. And what this expression says is represented by this curve, which is the ratio between the motion at the bottom and the motion of the top as function of frequency. And the key point of this plot is to show that below the resonance frequency of your pendulum, it's like if you were attached to the ground, so there is really no isolation. But above this resonance frequency, your mass behaves like a free mass. And this might not be totally convincing, but then the movie will convince you. And here it is. So the tops move a lot, but if you are above the resonance frequency of this, the bottom doesn't move. Great. So all the gravitational detectors in the world are using this concept. And if I ask you, what would you do if you really want to attenuate this motion by a lot? We just do a cascade of pendulum. You put one after the next, and so the bottom is now attenuated by this factor 1 over frequency square as many times as you want, such that when you arrive around, let's say, 10 or 20 Hertz, which is where you want to start detecting gravitational waves, the seismic noise, so the motion that your suspension is whatever, even if it's here, is actually this point is attached to the ground. And so you want to make sure that you can isolate this bottom mass as much as possible. And so this is how the LIGO and Virgo suspensions look like. This is the LIGO one. You see clearly 2 stages, so those are the last 2. There are 2 more, and then there is actually another, we call it active isolation system on top, that each stage is kind of a layer of attenuation. The Virgo system is even more impressive, in my opinion, is essentially 7 stages. And in fact, if you then try to plot the seismic motion in meter over square root of Earth as function of frequency, you would see that starting, I think in Virgo they claim 1 Hertz, you get, by the time you arrive at 10 Hertz, you have got 7 times 1 over f squared attenuation. So your noise at the top is attenuated by 14 order of magnitudes by the time you arrive at the bottom. And so this is, in our field, is like to say, okay, then the mirrors don't really move in the gravitational lace band. They move, if you were to look here at below 1 Hertz, they move, they are attached to the ground, but above that, they don't. Okay, the other piece that I was talking about is high laser power. Why these interferometers have a lot of laser power circulating. So let's do some math again for those who liked it. And if you don't like it, I would just give you the message. The message is you need a lot of power. So here is your Michelson interferometer, and then you can start if I say, okay, this is the laser, and there is the electromagnetic field of this laser, which is called E in, and I want to calculate what E out looks like. Then you can, depending on how far you are in your studies, you might find this obvious or totally obscure. That's either way is fine. If it's obvious, then you can start propagating this field here. This is the beam splitter. It splits the light in two ways. And then you accumulate the phase in these two arms, and then these mirrors reflect back, and then you calculate what is the electromagnetic field at the output. And if you do that, and this is a piece of the math here, then the important point is, as you try to write down the power at the output of your interferometer, you see that is a function of the differential phase between the two arms. And that's the key thing, because that's what you want to measure. So a Michelson interferometer senses the differential phase of the two arms, which is what the gravitational waves does. That's why we use a Michelson, or at least one of the reasons we use a Michelson. And then you see that this is the first component, it's the sinus square of the phase multiplied by the power that arrives on the beam splitter at the input on this side. And then at this point, you can calculate what is the signal, so the sensitivity to this differential displacement over the noise that you have. And this is where you get the insight of what you need to do to have the best signal to noise. So your signal is essentially derivative of the power at the output with respect to the differential phase. And your noise in this system is shot noise. So is the noise due to the uncertainties in the arrival times of the photons at your photodetector. So it's a fundamental noise which is due to the quantum nature of light. And it's in every experiment that uses light. And so this shot noise is proportional to the square root of the power at the output. And if you substitute for this expression, you see that then is proportional to the square root of the power on the beam splitter. And so then the next step, where everything is the same, so this is signal and this is the shot noise. And if you then try to calculate what's the signal divided by the noise, you see that this quantity is proportional to the square root of the power on the beam splitter. And so if you want to maximize your signal over noise, you want to put as much light as you want. You would see that there is this other piece here, which is the cosine of the differential phase between the two arms. And this is now a bit tricky, because if you look at this expression, you would think that, great, if this phase is 0, this is 1, and I maximize my signal over noise. But then, if you actually go back, you see that if the phase is 0, that your sinus is also 0, and then you have no signal. So really operating at the point where the differential phase is really 0 is not a good point. So you do not operate at the bottom of this parabola, which represents the power at the output of your detector, but you go a bit off. So you do actually get some signal there. This is already quite complicated, but this is just to give you a sense that it's not as easy as saying, great, my mirrors move and I get a signal. It's actually, if you try to write down the equation of what is the optical response of your interferometer, things get complicated very quickly. Okay, so in the story of this field, several detectors in the world were built, and until in the early 2000s, so we usually, in my talk, I will mostly talk about the two LIGO instruments, Hanford H1 and Livingstone L1. So those are two acronyms that I'm going to use. And then we're going to talk about the Virgo detector. At that time, there was one in Japan, which is called Tama, which was only 300 meters. And so it was the most sensitive detector in the world in like 2002. But then when the bigger detectors started operating, was then put out of commission. And then there is a 600-meter detector in Germany. Virgo is a 3-kilometer arms, and the LIGO detector is 4-kilometer arms. And so those are the most sensitive detectors, were also the most sensitive detectors at that time, but they were not sensitive enough. And so there was no detection for many years. That's why no one actually really knew about this field to start with, because they took data, they didn't detect anything. So if you start to go a bit more in the detail of the instruments, from the outside, they pretty much all look the same. This is the central building where your laser and the beam splitter is. And then for LIGO, this is Hanford. 4 kilometers away, there is an end station here and here. And you'll see that later on, I'll show that the optical configuration is not as simple as a Michelson interferometer. It's actually a bit more complicated. If this is the Livingston detector, again, from the outside, it looks pretty much the same. And the Virgo one, the only main difference is the 3 kilometers arm instead of 4. If you go inside this building, you would see chambers like this. And those are the chambers that host the mirrors. So the mirrors hang inside the ultra-high vacuum system, and the light propagates through. Next layer of details, a schematic of the advanced LIGO detectors in 2015 after the major upgrade to make them more sensitive will look like this. So again, until 2015, the instruments were not sensitive enough. In 2010, actually, all the instruments, LIGO and Virgo, went down, Virgo in 2011, for a major upgrade. And when they came back in 2015, that's how they looked like. The basic improvements were that the pendulum that showed became way more complicated. And those are the ones that I showed you before with the 4 stages and the isolation on top. The mirrors are 40 kilograms, high-quality fused silica mirrors. The laser operates at 1064 nanometer wavelength, and in the first observing runs, we were injecting something like 30 watts of light. And then, before I just showed the Michelson, the actual optical configuration of LIGO and now Virgo is more complicated. The full name is a signal recycled power, signal and power recycled Michelson interferometer. It's quite long. And so the basic idea is that, first of all, you don't just have a mirrors at the end of your Michelson. You have Fabry-Perot cavities in the arms. And the function of these optical cavities is to enhance the displacement produced by the gravitational waves. And then you have one in each arm, and then the light would come back toward this way, but since the light is so important, because I showed you that the more light you have, the more sensitivity you have, then you put what is called the power recycling mirrors to send the light back in. And then at this point, you have a coupled cavity system, and that's why it's a bit complicated then to do the math that I just showed you earlier. It becomes complicated quickly, and if it was not enough, our own Alessandra and Chen, so the famous Bonanno and Chen, came up with the idea that actually you should put a mirror also at the output, and in this way you can modify the bandwidth of the instrument, so the sensitivity of the instrument in what is, let's say, the bucket. So, with all of this, then there is maybe this misconception that, okay, great, I just build the instrument, I put everything in, and then I don't know, there is a key, or I push a button or something, and everything works. That's not the case, because this is pretty much just the beginning. You have installed everything, and now you need to make all these cavities resonant with the incoming light. And all the mirrors that you have, you need to control relative to each other and relative to the laser beam. And you need to control it in what we say longitudinal degrees of freedom, so length, but you also need to control all the angles. All the mirrors need to point to each other at very high accuracy. So overall, that's one piece, and then all of these suspension systems are great above the resonance frequencies, but then you have all of these resonances that you need to damp. So overall, there are something like 300 control loops that are needed to keep the interferometer optimally running. And this is the control room at Livingston, and you see we monitor. There are sensors pretty much everywhere and cameras, and we monitor the resonance condition of the light inside the interferometer, and there are signals that tells you how much the ground is moving, if there is an earthquake, if there are microseism, whatever. Pretty much everything is monitored. Once everything is installed, then you can almost entirely control things from the control room, unless something breaks. So the result is that then at the output photodetector, what you have is, the gravitational wave signals, sure, plus all of the noise that you have reintroduced while you were trying to control the mirrors to keep them in the right position. So now I have a movie that goes a bit deeper in the complexity of this system. Those are the only mirrors that we usually show. But then the reality is more like this. Let's see if this goes. Okay. So this is the Hanford site, and this is the central part where your laser and beam splitter is. And it's not really just the laser, as you would see in a second. So this is the vacuum system and the chambers that I showed you earlier. Here is the beam splitter, and now we go back at the point where the laser enters the vacuum system. So the laser is here and enters the vacuum system. And then you have, first of all, call it input mode cleaner. So it's a cavity that conditions your beam as it comes in. And this is the power recycling mirrors, but it's not just one mirror, actually. There is a telescope that you need in order to prepare the beam to match, to match the fact that you have a 4 kilometers arm. It goes to the beam splitter, it's split into two, and then we're going to zoom out for a second, and we're going to the end station. Here, this is your Fabry-Perot cavity where the lights, it's like if it was going back and forth many times, and that's how you enhance the gravitational wave signals. And then we go, 4 kilometers away. These are the valves that helps you to isolate the vacuum system. And this is your main optics. This is the end mirrors. We call it test mass sometimes. Here is it's only just one piece of what's in there. And now the light comes back to the beam splitter. Again, this is what we call the dark part. It's not as dark as you would think, actually. But so it's not the end of the story. Then you need another telescope to make the beam size right. And then you have some steering optics, and this is the final cavity. It's called output mode cleaner. Again, it cleans the mirrors more, and after that you have the photodetectors. So that's what's really inside. So usually when we talk about the suspension system, we talk about seismic noise, but there is another important fundamental noise that limits the sensitivity of this instrument, which is thermal noise. This is actually, any mechanical loss that you have in the way the mirrors are attached. And both LIGO and Virgo use fused silica, very high quality factor fibers to suspend the mirrors, which is kind of crazy because you say, well, it's a 40 kilograms optic and is, and these are the fibers that are actually sustain it. But it took several years to develop this technique, but now is actually working pretty well. It's not just the thermal noise in the suspension, it's also the thermal noise in the optical coatings that you need on your optic to make it very high reflective. And so there is the Brownian motion of the molecules of these coatings, which is actually a source of noise. These mirrors are also state-of-the-art optics, so we kind of drive that industry, let's say. They have only few part per million loss, and the absorption is also extremely low. So I was telling you at the beginning the story that I walked in the Virgo control room 20 years ago, and the interferometer was not working. So this is actually a slide from my PhD thesis presentation. The first job that we had to do at that point was to control the longitudinal degrees of freedom of the interferometer, or length. So how you can make all these cavities resonant with respect to each other. And the way in which you do this is, I think, a clever technique. We call it it's called the Pound River Hall technique. So you do not inject only the main laser beam, which is we call it carrier, but you inject what they're called sidebands, which are fields separated in frequency. So usually the sidebands are at around several megahertz. And then the key thing is each of these fields has different resonant conditions in the various cavities. So for example, the carrier field is resonant in the Fabry-Perot cavity arms, but the sidebands are not. And then when you beat this field into each other at the various output ports of the interferometer, you can extract an error signal, which is 0 at the operating point where you want to be. And so this is the plot that shows is in nanometer and arbitrary unit. This could be power, or you could also calibrate that in meters. And the signals look like this, and there is a 0 at the resonant conditions. And so then what you do is a feedback control system where you take this signal at the various cleverly at the various output ports. You filter them. Some are digital filters, some they're very fast, you need analog electronics, and then you send correction signals to what we call actuators, so something that allows you to push on the mirrors and move them around such that you pretty much put them where you want. So this is an example of the mirrors, of the actuators that were present in Virgo. There are different types. But anyway, the point is that if it's not, the thing that the point I want to make here is that when you do this, that's great. You can then control the mirrors and put them when you want, but you're also introducing noise pretty much at each step. So your sensors have some noise. Your actuators have some noise. So you put the mirrors when you want, but the price that you pay is that you're also reintroducing noise in the system. And so when then you try to then look at what is the total noise of your instrument, then you end with something like this. So this is a plot that you have seen several times yesterday, but let me spend some time say again what it is. So you have frequency at the x-axis, and then on the vertical axis you can plot the amplitude of the gravitational waves that you could detect, but you can also, that's what we actually do, you can calibrate this in meters, meter over square root of Earth. So this is displacement. So this is essentially the noise of your instrument. And we like to plot it like this rather than looking at it in the time domain, because that gives you information of which frequencies you have, which noise. And with everything that I've told you earlier, you have now the ingredient to understand all of these noises. So in brown here is you don't almost not see it. This is the theoretical seismic noise that we also call the wall. There was a question yesterday, how early in the universe you can detect gravitational waves. And this is essentially the limit on Earth, is that the mirrors are at the end attached to the ground, and so you cannot go much below. We think in the future, that you can go from, let's say, 10, 20 Hertz to 1 or 5 Hertz, but much lower is really hard to do on Earth. Then you have the thermal noise that I described earlier. This is due to the coating, and this piece is due to the suspension. This is all in green. And then the gray one is this, what we call technical noise, which is pretty much the sum of all the control noises that we have. Could also be some other nasty noises that are, for example, a famous one is scattered light. So you have all this light going around, and there are some ghost beams that can find a path back to the main photodetectors, and that cause noise. So all of this is grouped in technical noise, and this is the thing that we usually don't like to talk about in public. It's like, it's like your dirty laundry thing. We don't talk about it. And then there is one of the main noises, this blue one, is quantum noise. I explained earlier the shot noise. So again, this is due to the quantum nature of light. There is an uncertainty in the arrival time of the photons at the main photodetectors. There is another piece at low frequency that comes with this, which is radiation pressure noise. And this is this piece here, which is, we'll talk more later. This is also very interesting because it's not the radiation pressure, it's not the classical radiation pressure noise. It's not the fact that you have a lot of light that pushes on the mirrors that cause you problem. Well, it does, but it's not this noise. This is really the uncertainties in the quantum uncertainties in the momentum of the photons impinging upon your mirrors. So this is and it's kind of remarkable that these instruments are so sensitive that noises like this are actually relevant. So all of this together adds to this, what we actually measure, which is this red trace here, which is all the total noises. And all the traces that we put here is us trying to understand what our noise is. And then in all the detectors in the world so far, if you are clever and you sum all of them, you would see that there is always a gap between what you measure and what you really understand. And those are, we can call it unknown noises or mystery noises. And so there is always a bit of a discrepancy between what we understand our instrument and what the instrument actually does. Okay. So to put this back in the context of the strain noise that Dario and Alessandro talked about yesterday, earlier we had displacement, so it's your delta L. You can then divide it by L, and you get your H, the astrophysical relevant parameters. So in other words, strain noise is detector noise expressed as equivalent gravitational wave strain, H. I don't know if this was obvious to you already, but to me, it took me a while to kind of deeply understand this. And this is again expressed as a function of frequency. So if we go back then to the story of this field, in 2015, the LIGO detectors noise, or strain noise, was represented by these blue and red traces of the Livingston and Hanford detectors. They were about 3 times more sensitive than the best noise ever measured before by what we called initial LIGO at the early 2000s. Not quite as good as the design of advanced LIGO, but it was pretty much good enough to open the field of gravitational wave astronomy and to make the measurement. One would say, well, it's only a factor of 3, why it's such a big difference? there is a important point of these detectors is what you measure is equivalent to the distance in the sky at which you can detect the source. But then of the events that you can observe scale as the cube, right? Is the volume in the universe that you observe. And so there is this tension of always trying to make the sensitivity of your instrument better because you gain with the cube. So if I make my sensitivity better by a factor of 2, I have, roughly speaking, 8 times more higher chances to detect something. And so every time you see this ball here is to remind you that that's the volume in the sky that matters. And so here it's hard to see, but this little ball here was initial LIGO detectors, and then the advanced LIGO was 10 times better than LIGO, but that means 1,000 times higher chance to detect something. So this is so you know then the rest of the story. LIGO detected gravitational waves, great. Since then, there has been a sequence of observing run and improvements to the instruments. I show you we have not yet reached design sensitivity. So there was always this work of try to do better, and I will show you what exactly is happening. So the gravitational wave network today includes not TAMA that I mentioned earlier, but another Japanese detector, Kagra, which is 3 kilometers underground. And Kagra is developing new technologies, so they do not use fused silica for their mirrors, but they're using another material, which is sapphire. And their goal is to operate at cryogenic temperatures. I will talk a bit more later about this. But because of this reason, there is a lot of work that they need to do, and they do not have a sensitivity which is astrophysically interesting yet, and probably they won't have one for quite a while. And then it was mentioned earlier that pretty much thanks to the discovery, or at least the discovery contributed to the approval of a third LIGO detector in India, which is currently under construction. And then the usual LIGO and Virgo. And Geo 600, which is also doesn't have a sensitivity which is high enough for binary sources, because it's 600 meters. So here I have a same plot that I showed earlier, displacement versus frequency, so the noise of your detector. This is the best displacement noise ever measured so far. And this is the Livingston detector during the last observing round 3, which ended in March, ended early because of the pandemic. And so here is a progression of noises. So O1 is the first observing run, and then the second observing run, and in blue you see is the third observing run. And again, here is a collection of all the noises that we do understand of our instrument. And then, again, there is always a bit of a gap between what we understand, which is this black trace here, which is the sum of all of the noises that we know we have, and the blue, which is what we actually measure. And this little gap here is something that many people at the observatories are trying to reduce and make zero. So here I want to go back quickly to some of the key concepts so then you understand what is the work that is happening at the observatories now. So we talk about quantum noise, which is, unfortunately, every slide is a different color, but so now is pink, which is here. So shot noise, we said earlier, improves, so your noise to signal, if in some sense, goes as 1 over the square root of the power. So the higher the power, the lower is this noise. So there is this effort in always trying to increase the power in your interferometer. Unfortunately, as you do that, then your radiation pressure noise goes up because it scales as the square root of the power. And it's also inversely proportional to the mass of your mirror. So, in fact, the way in which advanced LIGO was designed initially was to pick the mirror's mass as large as possible to compensate for that. And then I talk about the coating thermal noise here. That's, again, due to the materials that you need to coat on the top of your mirrors to make it high reflective. And that's as a function of the mechanical loss of the mirror coating, so it goes as the square root of that, and the square root of the temperature of the mirror. And so that's explained why, for example, if you one, at least naively, one would say, great, go to cryogenic temperature so you can make that lower by reducing this factor here. So after, I didn't say earlier, but under each of these curves, you see a paper, usually several PhD's theses of students who devoted their PhD time to either understand a piece, maybe a couple of these noises at the LIGO site. I talked about cryogenics in CAGRA, again, because the coating thermal noise scales as a square root of the power. One idea is, great, let's go to cryogenic temperature. And that's what CAGRA is trying to do, and the goal is to reach 20 Kelvin. As I said, this is becoming, I guess, even a bit more challenging than they originally thought, and they're having a lot of technical issues that they're trying to overcome. So you should not expect significant sensitivity, I think, for a few more years. And then there is another concept in LIGO, we call it Voyager, and the idea is not to go at really low temperature, but to use a property of a new material, which is not sapphire but silicon, which has interesting properties, and it would be beneficial to go at something like 125 Kelvin to improve the performance of the system, and we can talk more. The problem with this is you also need to change, so as you change material, you need to change wavelength, and then it becomes a lot of new technologies that you need to test. I'm not sure exactly how much I've left, but I will keep going until someone stops me. Say again? Great, okay. Okay, so now we have, if you're still awake at this point, you have all the ingredients to understand what is the work that is happening now in LIGO and Virgo. So one of the main efforts is to increase the power in the arms. So in O1 and O2, there are something like 100 kilowatts in the arm power, in the arm cavities. For O3, we managed to improve it by a factor of 2, and the goal is to gain another factor of 2 for O4. The advanced LIGO design is actually even 2 times higher than this. But it's quite hard to increase the power. First of all, you need to have a high-powered laser, which we now have, but it took actually several years because the first version of the laser didn't quite work as expected. And then you need to make sure that you're able to compensate for the thermal lensing that happens in the mirrors when you have all of this power. And so we have what we call a thermal compensation systems that make sure that the radius of the mirrors remain close to the nominal values. You have control issues because this is now all the classical effect of high power. So the torque, so if your mirrors are not perfectly aligned, the power of the laser is enough to induce a torque in your mirrors, and so you need to compensate for that. There are also some other nasty effects, like imperfections in the coatings that when you put a laser beam on become power absorbers, and then they distort your beam. So there are a lot of technical problems that we think we have a good handle on it right now, but that explains why going to the nominal advanced LIGO design power is hard. Because it's hard, there is a complementary approach that emerged kind of in the last 2 decades, really. Mainly 3 professors in the world, MIT, Germany, and Australia, recognize that quantum optics, in particular squeeze states of vacuum that were produced in tabletop experiments in the world, had the potential to help reducing quantum noise in gravitational wave detectors. And so this is the transition of my talk, in which I'll start to talk a bit more about this. If you have not heard about squeeze light, and if you do not have a background in quantum optics, you maybe think I'm crazy. That's what I thought when they told me I should work on this, just to be fair. So if you do not get it, we can talk more later. You can find a lot of materials online. Sometimes to make us feel like we are less crazy, we don't really call it squeeze states of vacuum. We call it squeeze states of light, because at least, you say, okay, you are manipulating light in some way. But actually, no, really, you manipulate vacuum. And for vacuum here, we mean the vacuum fluctuations that are around us. So if you have I think the technically correct word is 0-point energy fluctuation. So even when there is not an electromagnetic field, or like the amplitude of electromagnetic field classically is 0, the energy is not 0. It's equivalent to say that the ground state of a mechanical oscillator has energy. Does that sound familiar to some of you? I see someone nodding. Like this, or? Yes, okay, great. I talk about these things like, oh yeah, obviously, who didn't know about this? It's actually, there is always someone who thought about it, and then we take it for granted because there are several papers written about it. But so the intuition in the 80s was that the way in which we describe quantum noise, which is the way in which I've just did it earlier, saying, okay, the quantum nature of light, you have these photons who goes around at high frequency is the uncertainty in the arrival time of the photons at the detectors, which cause shot noise, and low frequency is the uncertainties in the momentum of the photon impinging on the mirrors that cause noise. Great. All of this gives you some, tells you the right thing. It tells you, great, if you have more power, you win at high frequency, and you lose at low frequency. But that's it. So the insight of this picture is it gives you a new way of reducing quantum noise, and that's what I'm about to explain. And the insight is that, forget about the light. What is really causing quantum noise in gravitational wave detectors are these vacuum fluctuations that are everywhere, and they are everywhere, and the impact in our daily life is negligible, but they enter everywhere where there is an output port in your in your instrument. And in particular, the largest coupling, let's say, is from what we call the dark port. So they enter here. So basically, what happens is you can represent these 0-point energy vacuum fluctuations with 2 components, which we call quadratures, that are in some sense equivalent to the amplitude and phase of your field. Even if the coherent amplitude is 0, you can still represent your squeeze field, your vacuum fluctuations this way. And so, again, even if the amplitude is 0, there is some noise associated with that variable. And with following the Heisenberg uncertainty principle, these variables, which again we call quadratures, are associated with amplitude and phase. They enter the interferometer. The ones that matter most are the one from the antisymmetric port. And they are those vacuum fluctuations that are pretty much responsible for the fact that your photons are not really ordered well. And then these vacuum fluctuations beat against the light in your detector, and what you then see is that if you try to represent your interferometer signal in this phase and amplitude plot, then you see that you have noise, which is both in the amplitude and in the phase. And this is the noise that you are trying to reduce. This is the shot noise that you don't want. So why this picture is powerful? It's powerful because it tells you that, great, if you could reduce this noise, instead of injecting vacuum fluctuation that, they are there. It's not like you are intentionally doing it. But if you could replace this vacuum fluctuation with something that has less noise in the quadrature that you care about, so in this plot would be the axis that is aligned with your interferometer, then you win. And that's what squeezed states do. And so this is the idea. You reduced quantum noise by injecting squeezed vacuum, so you have less noise or less uncertainties in the axis that you care about. The Heisenberg uncertainty principle needs to be valid, and so if the noise gets smaller in one quadrature, then it gets bigger in the other. But for the advanced LIGO detectors until a few years ago, this noise, the radiation pressure noise, if you remember, radiation pressure was much lower with respect to other noises we didn't care. And so that's why this becomes an interesting and doable way of reducing quantum noise. And then the other piece is that you can adjust the relative orientation of this noise, squeezed vacuum noise that you have, such that you align it, as I just explained, with the you lower the noise in the axis that you care, at the expense of making the noise higher on the other. So this is a lot of information, and I wouldn't take it personally if you don't believe it. That's fair. But let me just say, so this seems very abstract, and then at the end, like, okay, great, but what you actually do? So you build a device which we call the squeezer, and what the squeezer does is able to take some random vacuum fluctuations and convert them in these squeezed vacuum states. And then we take these states and we inject them in the interferometer. How you practically make squeeze fields, the word to look for on Google is optical parametric oscillators, OPO. It's a cavity, and then the thing that makes the magic, we say, is a crystal which has a strong nonlinear component. So you can pump you can pump this cavity, and you pump the crystal, in our case, with green light at twice the frequency you actually want, because then we want to, so you pump at 532 because you want your squeeze field to be at 1064 nanometer. And the way in which, so this is the math, but we can talk about this maybe offline. The way in which I understand squeezing is that, is this way. The way in which you can think about this OPO, so this cavity that produces squeezing, is that is an object that makes a copy of a sidebands that arrives to it. So this is you remember we talked about carrier sidebands before. You have random vacuum fluctuations that enter your device, and that makes a copy. But it correlates these new sidebands that is produced, and then they move together. So it's like, imagine that you have these vacuum fluctuations that are kind of randomly going in. What you do is then you actually fix each of that and you make a copy, and at this point they go together. And it's this correlation that allows you to reduce the noise in one quadrature with respect to the other. Again, this is mostly to spark your imagination and your interest, and then you can go online and find a lot of material. If this is it's interesting at all. The way in which then we build this is, so squeezing was, again, because of this problem with increasing the power, and then this idea that, okay, maybe we can reduce quantum noise, not just increasing the power, but also injecting squeezing. Squeezing became a technology that several groups in the world, as I said, started working on. And the Geo Detector in Germany started now more than 10 years ago developing this technology. We also did a test in one of the at Hanford in 2010. And this technology seemed promising, and so we decided to deploy it for the last observing ground on 3. That's the work that I led. That's why I'm talking about it. So I think it's one of the coolest things ever. Totally unbiased opinion, obviously. So we build a system like this. So we put this OPO, this is the crystal that does the magic, and we put it here. This is another platform. You probably from far you just see a bunch of metal, but these are all optics. This is Faraday isolators are all optical components that need to condition the beam before it goes in the OPO. And then there is a beam, the squeeze beam, which is really the squeeze vacuum. So if you put a card on it, you won't see it. So we use a proxy for this beam. This is another story that I'm happy to discuss offline. Here it is. We inject, this is your squeezer, this is the OPO, and then you produce squeezing, and then you inject it at interferometer dark part. This is the signal recycling now. So this is just to orient you in this picture. This is the main laser, the power recycling, those are the cavities. The squeeze beam comes and then enters the interferometer and then propagates toward the output mode cleaner and then goes to the photodetectors. Those are the ones that sense the gravitational wave signals. So I want to, since I followed the development of this project from the beginning, I want to give you a sense of what it takes to do something like this, and I want to also highlight the fact that most of the work is done by students and postdocs that carry this forward. So this cavity was originally designed at MIT, and this is the day in which we shipped. And this is our lead engineer, who was quite nervous that day. And we sent it to the Livingston observatories. This is Maggie. Maggie was at that time here. She was the lead graduate student who moved from MIT to Livingston, and here she is installing it. And this is the staff at the observatories to help integrating this system. And I like this picture, but it's also hard to see what's in there. This is the output mode cleaner that I talk about, and the main gravitational wave detectors, photodetectors, are here. And we put the squeezer next to it. And then the squeeze beam propagates here and then goes back to the main interferometer. So the squeezer had to work in the lab, in an optics lab first, and then he had to work and integrate it with the interferometer itself. That's not easy. So I just want to, this is the control room late at night, probably the first day that we made this work. We usually take pictures only when things work, so I think that's an easy. And it's late at night, and you can see my face to recognize that it's probably 2 a.m. given the state. So I talk about Maggie, and here is the other student working on this, Autun. She's from China, she's from US, and then Sheila is now one of the senior staff at the Hanford site. We worked together on the first experiments that use squeeze light in LIGO about 10 years ago, and now she's one of the lead commissioners at Hanford. This is Anna Maria. She is the equivalent of Sheila at Livingston. She has spent, I think at this point, maybe 15 years working on interferometer. She comes from Romania, And this is Adam. He did his PhD in Australia in a tabletop experiments and then moved to Livingston. And is now, both Anna Maria and Adam are the senior staff and they really know everything about the instrument. And this is me and Matt who were just trying to travel there to help during that time. This is just a very small sample of the people who are needed to make something like LIGO work. There are something like 45 people at the observatories that each of them has particular expertise in electronics, mechanical engineering, optics, computing, and all of that to make the system, and vacuum systems to make this work. And here is the result. So now the typical curve that now you are an expert on, this is strain noise and this is frequency. And now the black trace here is the noise of your instrument without squeezing. And the purple line here is the calculated quantum noise, where quantum noise, it's a model of where we expect the quantum noise to be. And again, this is shot noise, and it's really limiting the noise of our system. And here is radiation pressure noise, and it's quite far. Here in gray, you see everything that is not quantum noise, which is kind of pile up together in this gray trace. So you expect squeezing only to improve the shot noise in the way in which you have implemented. And this is the green trace when you do that. So what we say, it's a quantum enhanced sensitivity. It's a very cool name to say that we inject squeezing and we reduce the quantum shot noise. And so the noise goes down. We like to historically, how much squeezing you observe in your instrument is measured in dB. And so we measured about 3 dB, which is about 40% reduction in noise, which is a big deal because you remember everything, every improvement that you make, then in terms of ability to detect gravitational waves, it goes with the cube. So even if it seems small, then the impact is actually important. So I spent a lot of time talking about LIGO, but as I said, Geo had done squeezing for a longer period of time, and also during '03 they continued using it, and they actually reached 6 dB, which is really a factor of 2 improvement. So they show that is it possible to get a larger enhancement. And those are the plot that I just showed you for LIGO. And this is the one for Virgo. So as I said, 3 dB. The plot here is a bit more complicated, but kind of the same idea. The black trace is the noise without squeezing, and red is with squeezing. And maybe we should define some global color scheme so we all do the same rather than mixing it up. But that's what it is. Okay, so this is the very last part of my talk, in which I now go back to tell you what's happening now at the site. So I told you '03 ended pretty much with the beginning of the pandemics. The interferometers, both LIGO and Virgo, had to be shut down. And this is the status at that time. Interferometers, had squeezing in it, and they started to be limited by radiation pressure noise. And you remember, when you inject squeezing, you make the noise smaller in one quadrature, so you make the shot noise better, but then the radiation pressure noise gets worse, because you pretty much move all your noise out in the other quadrature. So if you then try to also increase the power, and you do squeezing at the same time, then the quantum radiation pressure noise is too high. So we need a cleverer way of doing squeezing to be able to keep increasing the amount of squeezing that you inject. We call this frequency-dependent squeezing, and I will spend some time talking about this. I told you already about how difficult it is to operate the interferometers at high power. In particular, I think the newest problem, I guess, has to do with point absorbers. And now the vendors actually have improved the process by which they coat the mirrors. And so in the most recent mirrors that were delivered to LIGO, this problem is actually largely mitigated. So we hope we won't see that in the next observing run. And then there are these technical plus unknown noises below 40 Hertz, and this is the gap between the noises we understand and the total noise. And then I talk about the coding thermal noise, and it's a problem in the sense that it's a fundamental limit in what we call the bucket, so the most sensitive part of our curve. And so there is a worldwide search for better materials to reduce the mechanical loss of this optic. Okay, if you still have some energy, quantum energy maybe, we're going to talk about frequency-dependent squeezing. So, strain sensitivity versus frequency. The purple curve here is advanced LIGO quantum noise at design sensitivity. What happens is, if you inject squeezing, the shot noise gets better, but then radiation pressure noise gets worse because, again, you are moving you cannot really eat this noise. You're just redistributing it. You are not violating Heisenberg uncertainty principle. So how can we still improve the high frequency without paying the penalty of losing sensitivity at low frequency? So the idea came in the early 2000s, by Kimball and others, and the idea is represented by this figure. So you have now your squeeze beam. Before injecting it in the interferometer, you should bounce it off what we call a filter cavity, which is yet another optical cavity that has the right property such that when the squeeze beam comes back, is optimized in frequency. And so if you inject, if you remember, this is pretty much you rotate the squeeze ellipse as function of frequency. And you adjust it such that this rotation is done cleverly in a way that then you get a broadband reduction of quantum noise. This is also sounds very difficult to grasp. And in fact, if you look at this paper, you probably won't really understand anything, at least the first time, because it's a quite difficult paper to understand. But that gives you an idea of what is for example, theoretical physics in a kind of different perspective. It's not about the general relativity, but is about the quantumness of interferometers that comes into play. So all of this sounds, again, quantum enhancement, very cool. At the end of the day, you need to build a filter cavity. And this filter cavity, for several reasons, needs to be long, such that the rotation of the squeeze ellipse is done at the right frequency. And for Virgo and for LIGO, it needs to be about 300 meters. So it's a new piece of equipment that had to be built. And it started to be built right after the end of the last observing run 03, to be ready for 04. So Virgo has already built this system. They already characterize it. It works. And so the new acronym for 04 is FDS, which is frequency-dependent squeezing. So it's a squeezing that is optimized over frequency. And this is so the logbooks of both LIGO and Virgo are public, so you can go there. It's hard to understand what's happening because there are a lot of acronyms typically. But so the message here was, today we measured for the first time frequency-dependent squeezing with rotation down to 40 Hertz, which is close enough for where you want your ellipse to rotate. So this measurement was not done with the interferometer, was done with a diagnostic detector, so to prepare your squeeze field before you injecting in the interferometer. So the Virgo interferometer is now not yet fully stable because they have added the signal recycling mirror, and they are still working on pretty much making it stable and operating at low noise. And I think Jan Arms will talk more about Virgo in a couple of days. So the funny part of this is that in LIGO we have kind of the opposite state right now. The interferometer is working, but the filter cavity is not yet built. So they do have the filter cavity without the interferometer. We have the interferometer without the filter cavity. So we haven't yet measured frequency-dependent squeezing with the interferometer anywhere. The reason why the filter cavity is not ready for LIGO is that we could not accommodate the filter cavity tube next to the main arm tube, but we have to build a new structure, which is big, and it's here. And during the pandemics, there were delays associated with, as everything, with the material delivery for this. But the squeezer works. So we had to move the OPO in another place to make it then work with this cavity. And this is now a very recent result. This is literally 2 days ago. So it's very preliminary. We still have to check that this was done correctly. But so this is the usual strain, noise versus frequency. This one is in dBs because I told you we like to measure squeezing in dBs. And now you can focus on the green and red trace. Green is without squeezing and red is with squeezing. Now we do not have a filter cavity, and in fact the noise at low frequency now gets worse. And so we are waiting for the filter cavity basically to make this noise goes down, and so we can win everywhere. Okay, so I think I'm getting close to the end. I just want to wrap up what's going to be the next few years for LIGO and Virgo, so you can follow. So the next observing round of 4 and then the following one of 5 are part of what is called A+ and Advanced Virgo Plus upgrades. So there are techniques like squeezing, which were not in the original design of neither of these detectors, and now they are part of this A+ upgrade. So there is the main thing are frequency-dependent squeezing that I just described and increasing the power, and then we hope that the following observing round of 5 we will have improved mirror coatings, and we can actually reach the full power of the instrument. Timeline has moved a bit, but now we are confident that we can hold this date is the March 2023, where and what needs to happen for LIGO is that we need to have this filter cavity built, and then we need to inject squeezing in the filter cavity and show that it works. And for Virgo, they have the filter cavity, but now they need to work on the interferometer. And when everything is working, that's when we can actually start the run. There is a public page. These are the progression of the sensitivity, and you can just look at the maximum range that we think this instrument will reach. So nominally for LIGO, the A+ maximum range is twice as the one of the advanced LIGO initially. And so basically both instruments, this is where we are for O3. The color code now is the same here. So green is the best we have right now, and then you see gray and purple is where we want to be for the next observing round. After that, we are here. So 04 will start and will last about a year, and then there will be a gap, again, to improve the coatings of the mirrors, and then there will be most likely a sequence of observing and improving, and then what next? So we are now at, let's say, a few years from now in 2028. The idea is, there are ideas now to what we're going to do next in these instruments, and the main point would be try to modify the suspension and get new mirrors that are heavier and larger, so we can improve the suspensions and the seismic isolation, and increase the laser power even more and get even more squeezing. So pretty much trying to do the best of the technologies that we have. Okay, so I have Now just 3 more slides with the final message. So I hope I didn't annoy you too much, and most of you are still awake. That's great. The message is that operating and improving ground-based gravitational detectors requires a lot of physics, engineering, a lot of determination, a lot of people actually. I mentioned only some of the fields that we require expertise on: optics, electronics, mechanics, quantum optics, material size, control system. I could keep going. We need simulation tools to understand how the interferometer behaves. You need to understand the noise of your instrument and all of that. And students and postdocs have historically and are today a key to the success of this field. And then from the big picture, current gravitational instruments will come back online in March 2023. They will alternate observing and upgrading for several years. To actually expand our vision of the universe, this won't be enough. So the current gravitational instruments, even with the upgrades that I've just described, can probe only a very small part of our universe. So from the inflation to today, if you're familiar with redshift, this is z equals 0, it's the present. With the current gravitational wave detectors, we probe only the region, let's say here. And if you want to go back and look at the formation of the first stars and see what are the gravitational waves out there, you need next generation of instruments, and you need new facilities to do that. And so this is just to say, come back to listen to Jan and Matt's talk, in which they will tell you what is the vision of the field for more powerful gravitational wave detectors that will come online. Hopefully not too far from now, not too long from now. My very last slide. I think you already get a sense, but somehow, since our field is associated a lot with general relativity and Einstein, there is a bit of this sense that great work happens by one person alone in a room thinking deeply about things. And this is certainly true for some aspects, but my experience, this is me collecting pictures in the control rooms around the world. This is about 20 years ago, actually. The great things and things that move things forward, at least in large collaborations like LIGO and Virgo, it's always a team of people who come together and overcome the challenges to make things work. And you can look at this picture and you can see that these people can look like you, no matter where we are, where you come from, and which language you speak. Thank you.
Questions?
I see at least two.
Thank you very much for your nice talk. I have 3 questions. The one is there any other method used to reduce noise besides the one you mentioned about squeeze?
Yes. The other one is it's basically shaping the optical response of your instrument. So, for example, adding the signal recycling makes let's put it this way, if you didn't have the signal recycling, your sensitivity would look like this. And the usual displacement and frequency. If you add the signal recycling, that's this. And so in some sense, you are lowering the shot noise response. And this is just one example. There are techniques that push this a bit more, and so playing with the optical response of the instrument you can, for example, you could have a response which looks like a notch. So your sensitivity is very good at just one narrow band. We can talk more, but basically yes, you can, and is shaping the optical response of your instrument.
Due to the quantum nature of light, could we ever reduce the quantum noise totally?
Practically no, because I haven't talked about the technical issues, but it's a good question. You could say, well, you inject infinite amount of squeezing, and then you could make your quantum noise, 100 times lower, and then you don't need to talk about it. That's a good point, but practically it's not possible because every time you need to send the squeeze beam to your interferometer. Every time your squeeze beam encounter a loss in a spot, vacuum fluctuations comes back in. So it's like you have your squeeze ellipse, but then there is more noise that tries to mix it a ball again. And so practically there is a limit at how much squeezing we can actually observe in the instrument, just because there are many optical components between your squeeze beam and the main photodetectors. Even the photodetectors itself, they are very high quantum efficiency and all of that, but they have 1% loss. So practically speaking, for the next generation of detectors that Matt and Jan are going to talk about, we hope we'll see 10 dB of squeezing. So it's a factor of 3 reduction. But going beyond that, it's really hard to do with, I think, in my lifetime. And I plan to live a long life. So.
All right. And the last question is, if we have any picture on how different kind of noises will be affected by LIGO detector.
By?
LIGO detector, the one in space.
Lisa.
Yes.
Yeah, my favorite one. Yeah.
All right.
So that's a very interesting question. I think there will be a talk about detectors in space, but then the basic idea, at least the macroscopic differences, are they do not have the seismic wall. So what we worry about a lot, which is how we filter out the ground motion, there is not that problem. The detectors works in a very different way because they do not have optical cavities. They do not need to amplify the effect of the gravitational waves because they can just have infinite, in some sense, almost infinite length. And so they do not have any of the complications that comes with having multiple resonant cavities. They also, for them, shot noise is very bad, but again, they do not care because they have these long arms. I think Stefano will talk more about it.
Thank you very much.
Thank you.
So thank you very much for this fabulous talk. So I have one question regarding this quantum optics. Are there or were there any attempts to include this optical solitons using nonlinear Schrodinger equation for this power loss?
Sorry, I didn't catch the keywords.
These optical solitons using this nonlinear Schrodinger equation, because I think these are the optical solitons and we can minimize the power loss, and it comes, I think there is a term in this nonlinear Schrodinger equation. So
I'm not sure if I understand exactly what you mean, but the loss I'm talking about are just the optical loss in the propagation of your beam through optics. So it's if you have a imperfect, for example, Faraday isolators. As you move your beam around, there is not 100% propagation efficiency. That's the loss I'm talking about. So I don't think Schrodinger equation help you. It's just a loss that every loss is an open port for vacuum fluctuations to come back. That's the limitation.
Okay, so we don't need to worry about these optical solitons.
No.
Okay. And the second question is like, how when do we expect this sensitivity to reach to be enough to detect this continuous monochromatic radiation from pulsars? Like what is the timeline? Maybe 5 or 6 years? Is there any
You
rough?
mean from pulsar?
Yeah, this continuous waves.
Yeah, maybe others should answer this. I think it's probably, I would say, several more years, but I will let maybe Patrick answer more precisely. Yeah, I mean, we remain.
So the answer is that it's unknown, and the fundamental reason is that my understanding from my theoretical astrophysics colleagues is that there is no theoretical lower bound to how smooth a neutron star can be, how spherical a neutron star can be, how axisymmetric. So in principle, I mean, it may be, depending on the neutron star equation, say that these non-axisymmetries that we're looking for are really, really small. But that said, I think Alessandra, in your talk yesterday, you quoted something like 100 microns is the best limit on non-sphericity to date from LIGO, which is really impressive when you're talking about measuring an object that's many light years away from you. So sorry, I can't give you a better answer than that. We may be waiting a long time, but we could be very lucky. It looks like Barry wants to comment.
That's for very mature neutron stars. If we could measure young neutron stars, they're likely to be more asymmetrical. The problem is the ones that are known from radio frequency, from radio telescopes, and they're mature. So those are the easiest for us to target.
So if I can add, the improvements that we see, that the ones that I've described, are of the order of a factor of 2, right? So from where we are now to at the end of 05, we hope would be about a factor of 2 better. And then in the, let's call it 06, we hope would be another factor of 2 better. And those, it's up to factor of 4, which is not much compared to the uncertainties in all.
Because we need 10 to the power minus 25, minus 26, I think, for continuous waves, something like that.
Yeah.
So, okay.
Yeah.
Fine. Thank you.
Yeah. So it's not like every time is an order of magnitude that opens up and you know what I mean? Like our improvements in these decades would be at most a factor of 4 with respect to where we are now. You need next generation of detectors to go beyond that.
Thank you for your very interesting talk. You showed us that squeezing actually helps to reduce Virgo noise, but we saw that some peaks were higher after the squeezing. So is that because of squeezing or because of unknown noise? And if it has to do with unknown noise, can't we use that fact that squeezing make those peaks go higher to understand where that noise actually comes from?
So if you are, maybe we can talk later at lunch or.
Okay.
Is this one that you?
No.
No, I think maybe, I don't know if I understood, but she's referring to these, peaks that you see. So maybe, I'm sure you can.
No, sorry. These are nothing to do with squeezing. Thank you for catching that. You would see.
Before that picture.
Say again?
Before that picture.
Before that picture.
Yes.
Stop me when.
Yes.
Is this one?
Here. I think no, it was before that. Or that was the
Stop
one.
me
I
when.
don't know.
I haven't talked about squeezing.
You had 2 pictures. I don't know if that was the last one that you showed.
So, maybe that's not the answer you want, but so these peaks have nothing to do with squeezing per se. Those are features of, those are the violin modes of the suspension, for example.
I want a picture that has the noise before squeezing and the noise after squeezing only for Virgo.
For Virgo?
Yes, only for Virgo.
This one then?
Yes, this one.
Okay.
Some of the peaks, the red peaks, are higher than the black ones.
Oh, here you mean?
Yes, there, and some peaks from the right side are a bit higher. After
This
the
one,
squeezing.
I see. No, I
Yes.
think those are just as, it depends exactly when these curves were taken. It's not like squeezing can do this. Let's put it this way. These are just features of the interferometers. And for example, there are like violin modes that can be higher or lower. So unless there is so usually the noise that squeezing introduced is typically in this region. I mean, here is the radiation pressure, is the fundamental one that we expect. And if there are noises that comes in, for example, with the control of the squeezer, that's a very good question. Like, it's possible that the squeezer itself reintroduces noise. And it's usually in this band here. But it's not sharp peaks like this. You would see, it's either a broadband noise or some scattered light, which is the typical. I guess you could have a particular scattered peak that comes in, but it's not this. Those are just the interferometer features that happen to be higher when this curves. Also, obviously, I haven't taken this curve myself, so you can ask Jan also if he has a better answer.